Scientists have mapped more of Mars than the ocean floor on Earth.
It's very cold, there's no light at all, there's crushing pressures. So how can life exist there? And yet it does, in great abundance.
In the past 20 years, deep-sea explorers and marine biologists have discovered thousands of new species and vast ecosystems. But the remotest part of the planet has also attracted massive interest from one of the biggest global industries: mining. The deep ocean floor is packed with minerals needed for a more environmentally sustainable future. But at what cost?
There's a possibility that we could lose species before we even knew they existed.
In the middle of the Atlantic Ocean, on board the RSS James Cook, marine biologist Kerry Howell and a team of scientists are mapping the unknown.
If you're thinking about what have we actually looked at on the seafloor, it's less than 0.001%. But you have to remember it's vast. It's 70% of our planet is ocean. And of that 70%, 90% of that is deep sea. So it's a huge, huge area and difficult to get to.
With the help of ISIS, a 4-ton vehicle, operated from the ship's control room, they can plunge to depths of 6 kilometers.
The deep sea is really classed from about 200 meters, and it goes all the way down to 11 kilometers deep, which is the bottom of the Mariana Trench.
The huge machine is fitted with 5 cameras and robotic arms which collect samples of marine life.
It's this huge ecosystem that consisting of many different types of habitats and species.
With every deep water mission, scientists like Kerry are able to build a better picture of the ocean floor and the areas that could be most affected by human activities.
So when we're out in the deep sea, we collect physical specimens, but we mostly are collecting video of the seafloor and of the animals in situ, so in their natural habitat, so that we can study how those animals live, how they interact with other animals, and the sorts of roles they have in that ecosystem.
These images also reveal the resources critical for a green revolution.
People have been looking at the deep sea as a potential source of metals, and particularly rare earth elements, that are useful to humans and are used in many electronic devices.
Mineral-rich deposits have been found in 3 different areas of the ocean. On abyssal plains, flat areas of the seafloor, are polymetallic nodules, potato-like rocks that contain iron, nickel, copper, cobalt, and manganese. Sulfide deposits with lead, zinc, gold, and silver have been discovered near hydrothermal vents, and some underwater mountains have rich cobalt crusts.
The metals that are contained within these resources, things like copper, lithium, are used in things like batteries. The argument that is being made is that we need these metals to help with the green revolution, so renewable energy sector particularly, electric cars, these sorts of things, use these metals in their production.
Current land mining practices are known to cause severe environmental problems, from loss of biodiversity, soil erosion, and pollution. Mining of some elements, such as cobalt, is centred in poor countries where children are known to carry out dangerous work. It's calculated that by 2050, demand for cobalt and nickel will be 4 times greater than the available reserves on land. Now, mining companies and some policymakers are making the case that the path to a greener future will have to include extracting these minerals from the ocean floor. Although it's more difficult, mining companies can extract the same metals from a single location on the ocean floor as they can from 2 or 3 mines on land.
If a country has mineral resource within its exclusive economic zone, so that's the area of ocean around the country that it's responsible for, then it's up to that nation's government whether or not they choose to use that. And Japan has actually just recently gone ahead and successfully demonstrated the first deep sea mining in their own waters. In international waters, so this is what we call the high seas, or the area is the seabed. That is managed by a UN authority called the International Seabed Authority, and it's managed on behalf of all of mankind and all nations.
The International Seabed Authority, or ISA, has issued 30 exploration licenses to hunt for precious metals. The Clarion-Clipperton Zone, a 6 million square kilometre area in the eastern central Pacific Ocean, is of particular interest. It is estimated to hold 3 to 6 times more cobalt in its reserves than all known land-based reserves combined. But the CCZ is also rich in newly discovered marine life.
I think one of the worries about deep-sea mining is that because we are finding brand new species in these areas, there's a possibility that we could lose species before we even knew they existed.
And some of those species can not only benefit deep-sea ecosystems, but human health.
The bacteria that are living in the sponges, we're interested in them to see what antibacterial compounds they produce.
On land, Kerry has teamed up with Matt Upton, a scientist with a specific interest in antibiotics.
Antibiotic resistance is a major threat. It's one of the biggest threats to global human health. So we need to find new antibiotics. Discovering antibiotics in natural environments was something that I was already actively doing. It's just that when Kerry came with the sponges, it seemed to be an opportunity to look at some really strange and unusual samples.
Deep-sea sponges have been around for over 600 million years and produce antimicrobial compounds that Matt hopes could be used to make new antibiotics.
We know for certain some of the things we found are new. We know for certain some of the things that we found kill the sorts of bacteria that we want to be able to kill, like Staph aureus and E. coli.
The very first sponge samples that Kerry gave to Matt produced astonishing results.
When we started this, we didn't know what we would find. So I was surprised that we found things that had activity that killed these and other bacteria. Some of the early work went really, really well, and we got some very encouraging results.
It's early days, but if Matt is successful, an antibiotic derived from the deep sea would be hugely valuable.
The biomedical potential of these samples could be immense, and so we need to look at the bacteria in those environments and look at the samples to explore that and understand that in a bit more detail before we go ahead and potentially destroy some of those environments and lose access to those medical benefits.
Successful mining applications may well be granted within the next few years. As with mining on land, mining the deep sea will most likely cause huge disturbances to localized deep water ecosystems. But the knock-on effects could be catastrophic.
The deep sea performs a number of services for people. It locks up carbon, which mitigates climate change. It absorbs heat. It recycles nutrients, which support our fisheries. And it's these other types of service that we get from the deep sea that we don't even think about. And I would like to see just a greater understanding of the potential impacts so that we can make a much more informed decision about whether we do or don't mine the deep sea.
With the demand for these essential metals ever growing, governments will need to weigh up the impacts of mining the sea against mining the land.
My role as a scientist is really to provide the information to society and governments and management organisations to help them to then understand the sorts of trade-offs they might be making when deciding about ocean use.
For protectors like Kerry, it's a race against time to explore and understand the secrets of the deep and ensure governments and mining companies know the risks of exploiting these pristine parts of the planet.
Hi, I'm Claire and I directed this film. If you want to learn more about the future of the oceans and the people working to protect them, then click on the link opposite. If you want to learn more about the Protector series, then click on the other link. Please subscribe and thank you for watching.